Howdy, everyone. Happy Monday. I hope you're all doing well and hope you had a nice weekend. I hope, too, you are fans of Aggie women's basketball and are happy to see how well they did. Uh, 10 years ago, A&M women won the national title, and the final game was one of the more exciting games I'd ever seen on television. A&M was playing Notre Dame. They had a 1 point lead with about 30 seconds left in the game, and they had the ball under their own basket with 1 second on the shot clock. So it looked like Notre Dame was going to get the ball just 1 point behind and a good chance to win. Instead, the ball was passed in to a young lady behind the 3 point line, and she scored a 3 pointer. So A&M had a 4 point lead, which Notre Dame could not overcome, even though they had the top-rated basketball player in the country at the time. The slide on the screen reminds us how huge the universe is. As I've been telling you, there are about 2 trillion 2 trillion galaxies, and many of these galaxies have something like 200 billion stars. So if you do the math, we're looking at something like 10 to the 23rd, 10 to the 24th, maybe even 10 to the 25th stars or planets in the universe. So I think it's pretty safe to assume there are lots and lots of other planets with intelligent life on them at this time. And of course, if they're a billion light years away, there is no way that we're going to communicate with them. We have our exam on Wednesday. It'll start 10 minutes before normal class time at 1:25, and you will have until 2:40 to finish. Some students have accommodation for handicaps, and then they can add on their extra time. 50% more would be 37 and a half more minutes if they like. The exam does have a couple of more difficult problems, but it's a 110-point exam. If you get 90 points, you're guaranteed an A, and the exam will be curved. So just do the best you can and study for it. Dallas, one of our graders, said he would be online to tell you a little bit about signing on or getting the exam from eCampus. So Dallas, if you're there.
Hello, can you hear me? Okay, so everyone can see my screen. The exam will be under tests and quizzes. This will show up at around, oh, I'm sorry, I haven't shared my screen. 1 second. Dr. Lonnie, do you end screen share so I can share my screen?
Okay, sure.
Here, 1 second.
Whoops. Where do I do that? Do you know?
I think I can manually do it.
Professor, on the bottom where it says share screen, there's a little arrow, and if you click it, you can say allow multiple sharing participant.
Okay, I'm going to the dots, looking at options.
Here, I've got it. And sorry, let me share my screen really quick. Can everyone hear me better now? Or is it about the same? Okay, sorry about that. So to take the exam, you'll first go to your course page, so your Chem 322. And the exam will be under tests and quizzes. So I made this visible today, so you should be able to see it. Of course, however, the folder is empty, but starting at the exam time, so it's starting at 1:25, there will be a little assignment here saying exam 1. This will have be a copy of the exam that you can download, and also where you'll go to upload your exam file. So it'll work the same way as when you do your problem sets. So you'll just scan your exam and upload it to the exam. Uh, uh, Upload it to the exam assignment. It's also unlimited attempts until the due date, until the due time. So say if you make a mistake on your first exam when you uploaded it, as long as you haven't turned it in late, you'll be able to submit another copy. Does anyone have any questions about this?
Dallas, I recommend put everything you just said into an email to everybody.
Yeah, I'll send an email to everyone today. Sorry, there was a message in the chat.
Okay, thanks. There are a couple of chat questions.
Yeah.
Someone asks if they can use an iPad or a tablet. Yes, that's fine. Someone asked if they would be on Zoom. We're not going to have Zoom on. We just trust your own integrity on this. So get the exam. When you're done, scan it or photograph it and then put it back on eCampus. If you're worried that you didn't get it in correctly, plan B is go ahead and email it to me or to Dallas. Preferably, it's easier if Dallas gets it because he'll be grading it, he or Conan. You don't have to print off the exam. The exam should be done on separate paper. But you're all mature students by now, so do it in a way that it's easy to grade. A lot of people get most of their points on partial credit, and so make sure we see exactly what you've done. If somehow you have a fancy computer program in your calculator that does the answer for you and just put down the answer and it's wrong, you get 0 credit. And if we don't really see the work that you've done, or if you haven't shown the integrals, you might also not get full credit. So make sure you show all the steps of your work.
And also, as another comment, so before you submit your exam, please remember to make sure that everything that you scan is completely legible. There have been some issues with problem sets where I can only see half of the problem, or it's so blurry I can't really see anything. So it'll be really hard to grade the exam if I can't make out anything.
Okay, any other questions on that? Okay, thank you, Dallas.
Thank you.
Okay, so today we're going to talk about stuff that's not directly on the exam, but we're still using some of the principles that we've discussed on quantum mechanics and atomic structure and so on. So just a reminder, we've been looking at homonuclear diatomic molecules where the 2 atoms in the diatomic molecule are the same. Chat question was, is the exam over chapter 7 and 8? That's correct. Your syllabus tells you which pages in the book are covered. And also, of course, in your lecture notes, it'll be the section on quantum mechanics and atomic structure. Okay, so we're using the molecular orbital theory, a linear combination of atomic orbitals, and for diatomic molecules, it's simple because we take exactly the same orbital on each of 2 atoms. So here's our example of oxygen. So we can take the 1s orbital on each of 2 atoms, push them together, we get a lower energy orbital, 1s sigma, this is bonding, and we also get a corresponding antibonding orbital, which we label 1s sigma star. Antibonding orbitals, as you can see from this diagram, are real orbitals. Many of you may not have heard about them before. Freshman chemistry typically doesn't teach them, but this is exactly the scheme that you come up with. When you put the scheme together, you can count up the total number of electrons in bonding orbitals, subtract the number of electrons in antibonding orbitals, take the difference between the two, divide by 2, and that's the bond order that you have. So if you do oxygen, you find you have an excess of 4 bonding electrons, and so you have a bond order of 2, just like you'd learn in freshman chemistry. But if you write a Lewis dot structure for oxygen, you would not realize there are any unpaired electrons. You'd think there are some non-bonded electrons in the system, and in fact, oxygen has 2 unpaired electrons, which makes it paramagnetic. And as I told you, that was once a problem for NASA rocket ships. So the more general picture is this one. And as I pointed out last time, the thing to be concerned about is what happens with a 2p sigma orbital. The energy of that orbital is higher than the 2p pi orbital if the number of protons in the nucleus of each of these atoms is fairly small. So let's see, lithium has 3, beryllium 4, boron 5, and so on. It's only when you get past nitrogen at a Z of 7 that the 2p sigma orbital drops below that of oxygen. So we see that in this diagram. So here's the 2p sigma, here's the 2p pi, being lower in energy. So other than that, this is just like what you learned in freshman chemistry, 1s2, 2s2, 2p6 for atoms. And so you can figure out where the electrons go, you can figure out the bond order, and you can figure out if there are unpaired electrons and is it paramagnetic. And as I mentioned last time, when the 2 atoms aren't exactly the same, but pretty close to each other, like carbon and nitrogen, 6 protons for carbon, 7 for nitrogen, the energy levels are still very close to each other, and you can still get pretty much the same kind of energy levels and described by the same scheme that you do. Also be aware that you can have ions of these things. You can make Cn minus. If you add an electron to Cn here, you would put an electron here and you'd see it's in the 2p sigma orbital. That's another bonding orbital, and the bond order would go up from 2.5 to 3. So it looked just like nitrogen, that you would have a net 6 bonding electrons. So make sure you understand this diagram here on the bottom to calculate bond order, the number of unpaired electrons, and so on. And then also look at these systems. NO plus is a very common ion. Those of you in the that would be in an inorganic course. I guess chemical engineers aren't. You would learn about this. It's very common to make things like NO plus Cl minus. So it's a good cation that you can have. You can also make O2 plus 2. And so if you look at the O2 molecule here, notice that we have 2 electrons in an antibonding orbital. If we can get rid of them, we're going to get a stronger bond. It'll become a triple bond instead of a single bond. So O2 plus 2 is very common, and you can make all kinds of salts with it. O2 plus Cl2 with minus signs, et cetera, et cetera. So you can learn a lot just by looking at this particular scheme of things. Okay, so here's a table that summarizes some of these things. Here's H2 plus that we talked about first, 1 electron, bond order of 1/2, H2, 2 electrons, bond order 1. On the right, the most significant thing is to look at dissociation energy. So an electron volt is about 8,300 wave numbers if you want to relate it to hydrogen. But you can see then that a half bond gives us 2.8 electron volts. A full bond for H2 is roughly double that. But this is certainly not going to be exactly linear. But whether you call something a half bond or a single bond or a 2.5 bond, it's just going to be semi-quantitative. So the strongest bond here, you can see the triple bond for nitrogen. It's got the highest electron volts 9.9, but a single bond for fluorine is 1.3 electron volts, and for H2, it's almost 3 times that. This goes back a little bit to the shielding that we talked about. Fluorine has a lot of electrons that in that outer shell repelling each other, and so it makes it rather easier to dissociate the molecule. But anyway, this is semi-quantitative proof of what we had going on. And here on the right, I had shown you what some of these schemes are for the different systems that you would have. O2 plus also exists, and here's experimental data for it that you can see. The one conclusion that I hope you all pick up from this is that strong bonds overlap from orbitals of at or about the same energy and correct symmetry. We're not going to talk about symmetry in the chemical engineering course, but obviously if you have 2 s orbitals that are identical or 2 p orbitals that are identical, their symmetry can match and you can make them combine fairly readily. I will show you cases where you might have mismatches later when we talk about other molecules. Here's a case of an example where symmetry forbids the combination of an interaction. If you try to combine an s orbital with a p orbital side to side, you can see the top part would try to create bonding, plus wave function to plus wave function, but the bottom half would try to cancel. So this would be net bonding. Molecules are smart. They try to find the best way to get to the lowest possible energy, so they don't do things like that. And if we were to talk about symmetry rules, then we would see how some of that works, but we don't have time in the course. I mentioned unpaired electrons several times. Whenever you have them, you get paramagnetism. The strongest kind of magnetism that you're all used to, picking up nails with magnets, that's called ferromagnetism, generally involving domains of iron atoms. Paramagnetism is also strong, but I don't know exactly, 3 or 4 or 5 times weaker than ferromagnetism. There's a third kind of magnetism called diamagnetism, and that comes from paired electrons, but that's 10 to 100 times weaker than paramagnetism. So we normally don't worry about diamagnetism overcoming paramagnetism when they're in the same molecule. They are in opposite directions, so diamagnetism does cancel out some of the paramagnetism. But here's an example. If you have 2 electrons, 2p pi x and 2p pi y, they go into separate orbitals. That's Hund's rule, and they don't wind up pairing to each other. They're in the same direction. So this would be the case that you have for B2 for boron. When I was about your age, the professors would tell us they don't really know whether the 2p sigma or 2p pi orbital is lower in energy because people had not been able to measure the paramagnetism. So this is not a common molecule to make, but since that time it's been made, people measured the paramagnetism, and so we know that this is the configuration that you have for the system. If you go to nitrogen, you can see all the electrons are paired. You have a bond order of 3, no paramagnetism. O2 looks like this, and we saw this in the diagram. It has 2p pi star with 2 electrons, but one of them is 2p pi star x, one of them is 2p pi star y, just similar to this case, except oxygen has antibonding orbitals. And so you wind up with a bond order of 2, and obviously I've got a mistake here, or I can't read my diagram. It should say the number of unpaired electrons is 2. For some reason, it's not on my screen, and hopefully it's on your screen when you see it. So liquid oxygen is paramagnetic, as we've said.
Professor, you can just scroll the bottom, and it'll be on your screen if you scroll the bottom tab.
Okay, well, let's just make it smaller. Yeah. Okay. Yeah. So here we have two unpaired, and then one each in the 2p pi star x and one in the 2p pi star y. So thank you for the hint. Okay, so I stuck this in your notes also. I think I showed this to you before, but basically all of this follows the concept of molecular orbital theory. We make linear combinations of atomic orbitals. Here's the term LCAO. And this is the method that's used for computational chemistry using the variational principle. I've also called it the variation principle. But here's the basic idea that we're going to take atomic orbitals, which here are labeled by the Greek letter chi, and we have chi sub I. There could be a very large number of these orbitals. For diatomic orbitals, we just take these in pairs. So we combine a 1s with a 1s, or a 3s with a 3s, or a 3p with a 3p, and so on. But you could have hundreds of these orbitals. And then for each particular wave functions, you have coefficient Cij, which tells you how many times you use that atomic orbital for a particular molecular orbital. So read this page and try to digest this and see what it says. But it's essentially a summary of what we've been doing for diatomic molecules. Now, next we're going to get into heteronuclear diatomic molecules. We're going to see that lithium hydride is going to be very different. And we're going to see hydrogen fluoride is very different because the atoms are far apart in the periodic table. But if we have carbon monoxide, cyanide ion, or the nitrosium ion, we can pretty much use the same scheme that we have had before. So to understand the distinction, what I've done is I've taken these diagrams out of a book, and here's a case for a homonuclear diatomic. I've indicated this could be N2, but it could be H2, or any place where we have two equivalent atomic orbitals. We create one bonding orbital and one antibonding orbital. In the favorable case, both of these electrons go down into the bonding orbital, and the electrons are equally shared by the two nuclei that we have. So in this case, it would be a nitrogen here and a nitrogen there. I've drawn a picture of this upper orbital. So this could be a 1s plus orbital here and a 1s minus orbital up here. Down here, this would be 1s plus and another 1s plus orbital that we're combining. So we're combining like wave functions to get the bonding orbitals, and we mismatch the plus sign to the minus wave function of the atomic orbital to get the upper orbital. Okay, so how does it change if we go to carbon monoxide? Well, luckily, we can still get nice orbitals because the orbital energies are still pretty close together. But the oxygen atom has a charge of 8 in the nucleus, so 8 protons, meaning it attracts the electrons more tightly than the carbon atom. Carbon atom has 6 protons. So you can see the corresponding orbital on the oxygen is lower in energy than it is for the more electropositive atom, as indicated here for the carbon. So when these orbitals are formed, we still get a bonding orbital and an antibonding orbital, but these electrons are going to be much more associated with the with the oxygen atomic orbitals. So effectively, that means we're going to spend more time on the oxygen atom, and therefore we're going to know the oxygen is a more electronegative atom. And so carbon monoxide would have this separation of partial charges. Partial negative on oxygen, partial positive charge on carbon. So in freshman chemistry, you learn a lot about electronegativity. I'm not sure whether you're told exactly why some atoms are more electronegative than others, but it basically goes back to nuclear charge and the shielding that we talked about when we talked about with atomic structure. But hopefully you can see the difference here between N2 and CO2 that you would have. Kind of a summary again, the best bonding comes from atomic orbitals of the same or similar energy. So for nitrogen, this would be a little bit nicer combination because they have exactly the same energy. For carbon and oxygen, they're very close to each other in energy, so it still gets to be pretty good orbitals. When we get to talking about hydrogen fluoride, then they're going to be fairly far apart in energy, and you might not get quite a strong a bond. They need to have a correct symmetry, which we won't talk about specifically. And it helps a lot if the orbitals are of the same size. So a little old hydrogen atom, 1s orbital, does not particularly want to bond to a 4p orbital of a potassium, for example. It does much better if the atoms are smaller. Okay, so here's another picture of the carbon monoxide. And you'll notice that here is the book nomenclature. I'm not sure if this is out of your book or another book. The book just likes to go sequentially because the book is saying, well, this orbital here from the 2s combinations is really not a 2s sigma. I, on the other hand, contend this is very close to being a 2s sigma orbital, and this is close to 2s sigma star. So we can best understand these orbitals with these particular labels that we have. So here are the pictures of the orbitals. Notice that the 1s orbitals have been neglected in this diagram. So wherever this figure came out of, the person that labeled these orbitals called this sigma 1. If they'd included the 1s orbitals, they would have had a sigma 1 and sigma 2 down here, and this would be sigma 3. So that's another reason I don't like that nomenclature. They have an arbitrary starting point. Notice, however, when they get to the pi's, they do switch from sigma to pi. So we have a pi star and a pi star orbital. So these orbitals look a lot the same. These are S-type orbitals being combined. Here are the 2s. If we mismatch plus to minus, then it's antibonding. The pi orbitals look like this, just like we have for nitrogen and for our homonuclear diatomics. And then this one is the bonding sigma orbital that we have. We have a chat question. Somebody is ahead of me, they want to know how it works for larger molecules, and that's what we'll talk about after we talk about diatomics. So we're trying to get your feet wet with diatomic molecules first, with homonuclear ones, which are easiest to understand. Now I'm showing you diatomic molecules which are close to being homonuclear, where the two atoms are the same, and we can still pretty much use the same scheme. So something I sometimes like to do in the second exam might be to say, consider the cyanide ion, Cn minus, assume that you can use the homonuclear scheme for it, write the scheme, tell me what the bond order is, tell me how many unpaired electrons there are, and so on. So CO winds up being very similar to nitrogen, N2, because it has the same number of electrons. 6 plus 8 for CO, 7 plus 7 for nitrogen, or 14 electrons. Okay, so here's our summary. It provides the bond order, the Aufbau method does, predicts the number of unpaired electrons, and somewhat later in the course, we're going to talk about electronic spectroscopy and how that gives rise to color in the universe. Whenever we see color in the universe, it's going to come from transitions between molecular orbitals, for the most part, sometimes between atomic orbitals. But for the most part, most of the color comes from electronic transitions, and very often from bonding orbitals into antibonding orbitals. Okay, so what happens when we go to heteronuclear diatomics, when the two atoms are very different from each other? So this first page has this diagram, but The book I took it out of kind of took a partial diagram, so I created my own more complete diagram for HF, and I think that will help you visualize the previous page much better. So we're going to take hydrogen orbitals on the left, F orbitals on the right. It's still a diatomic molecule. Fluorine has a +9 charge in the nucleus. Hydrogen has a +1 charge. So all of the fluorine orbitals are much lower in energy than the hydrogen 1s orbital. In fact, even the 2p orbital for the fluorine is lower in energy than the 1s. So here's our full diagram. The atomic structure for fluorine is 1s2, 2s2, 2p5, counting for the 5 electrons. Hydrogen is 1s1. Well, as you learn in freshman chemistry, when you get to larger atoms, you have a lot of inner shell non-bonding electrons, and the 1s and 2s orbitals for fluorine basically wind up to be considered non-bonding inner shell, and they do not change in energy significantly. So when we draw these orbitals for the molecule, the same atomic orbitals pretty much hold in the molecular system. I think I might have mentioned sometime back when we talked about atomic spectra and the Rydberg constant and so on. There are scientists who like to look at what happens to some of these inner electrons from 1s shells and according to the Rydberg formulas and things like that. But that's just kind of an extraneous comment. All right, well, fluorine has 3 p orbitals pointing in 3 different directions. And if you form a diatomic molecule, only one of those orbitals can point towards the hydrogen atom. And that's the one from which we're going to make a molecular bond. So it'll be a 1s to 2p combination. And I'll show you a picture of that. But 2 of the p orbitals will not be able to bond, so they remain non-bonding. Notice here's my nomenclature. I use an N to indicate 2 non-bonding p orbitals, a sigma for a bonding sigma orbital, and then when we form the sigma orbital from the 2p and the 1s, we also have to form a sigma star. So here are the orbitals we're going to make, the molecular orbitals we're going to make from atomic orbitals. We take the 1s, smush it into the 2pz. The black dot is where the nucleus is for the fluorine atom. And so this is what it winds up looking like. So this is all positive wave function. It has nothing to do with electron charge. It's the wave function sign. And then the minus sign winds up off to the right and peripherally, and we don't really care about it. But then there's a big area here, big volume, that we can put negative charge. We're going to wind up being able to put 2 electrons in here. They zoom around, and those 2 electrons are going to attract the 2 positive nuclei towards the center, and that's our molecular bond that we have for HF. Whenever we start from 2 atomic orbitals, we have to form 2 molecular orbitals. So this was the positive combination. We also get a negative combination. If we have to combine plus wave function to minus wave function, that function has to go to 0. That molecular orbital representation has to go to 0 in the middle. And so we have a big region of either 0 or very low probability. And so your sigma star orbital winds up looking like this. The electrons can still go here. And a typical question you might ask is, well, were the 2 electrons going to be here or there when you put them? Well, the answer is both, and it depends on probabilities when you look at it. Okay, so we get the p combination bonding, but I also said there are 2 p orbitals that can't combine. This to that would give us no net bonding. This added to that would give us no net bonding. And so we call this a non-bonding combination also that we have. Okay, so keep this picture in mind. and I'm going to go back to the previous page, and I'm just going to show you this middle part, and in fact, without the 2p orbitals that are non-bonded. So I think this is rather misleading without all those other orbitals, but I want to show it to you because there are quantitative numbers that people have made measurements from. The ionization potential for hydrogen is 13.6 electron volts. And that's the amount of energy it takes to remove an electron from the 1s orbital out to the ionization limit, theoretically where the electron is an infinite distance from the nucleus. The ionization potential of the fluorine 2p electron is 18.6 electron volts. So we know the relative energies of these very well, and we can place them on our diagram. The lower orbital here is where the 2 electrons go. This is the sigma orbital that we talked about. And calculations have been done, and you can see it comes out to be represented by 0.33 times the hydrogen orbital, the hydrogen 1s orbital, plus 0.94 of the fluorine orbital. So it looks like that the fluorine orbital is contributing 3 times more. But it's actually a lot more than that because the probability is the square of the wave function. And so these numbers would come out to be about 0.1 of the hydrogen orbital, 0.9 of the fluorine orbital. And so 90% of the electron density here for this orbital is on fluorine. And as you already no doubt learned in high school chemistry, when you have things like HCl or HF or HBr, they dissolve in water, form H plus ions and F minus ions. But in the vapor phase, then your structure looks like this: partial charge, a positive on hydrogen, but a very strong, excuse me, a very negative charge on the fluorine. So that comes from looking at this kind of computation here. So this, I think, is still pretty straightforward when we look at diatomic molecules. Okay, reading the caption, I called it 90% comes from the fluorine, but it's more technically 88% of the bonding is on the fluorine atom when you look at this. Okay, so I think that wasn't too bad. Again, remember that this is the full diagram when we look at it, and this is what the orbitals look like. So I think all of you can grasp that pretty readily. Now, you might not think so, but if we go to our next example, you'd think this would still be pretty simple. We're going to look at lithium hydride. So lithium is 1s2, 2s1, and I've included the 2p orbitals in this diagram. And hydrogen is, again, 1s. Lithium has a +3 charge in the nucleus, so its 1s orbital is lower in energy than that for the hydrogen. So you can see the hydrogen orbital higher. The hydrogen 1s orbital is lower in energy than the lithium 2s orbital. When we draw this diagram, we recognize that the 1s electrons on the lithium, again, are going to be inner shell non-bonded electrons. So we're not worried about them. And so we will keep them as non-bonded in the lithium hydride molecule. This is a vapor phase molecule that we can look at. So that takes care of the 1s. 2 of the p orbitals have this kind of combination where you get no net bonding, very much like the case we had for HF. So you'll notice the 2px and the 2py orbital, I'm not having them change energy, and I'm still calling them non-bonding. But then we're left with a problem. As far as symmetry goes, and to some extent as energy goes, both the lithium 2s orbital and the lithium 2pz orbital, The PZ orbital is the one that points towards the hydrogen. Both of them can technically bond to the hydrogen. So if this were an organic chemistry course, I would probably be telling you, we're going to form an sp hybrid, life is clear, and that's what's going to create the bond. But somehow we have to see how we come up with this particular diagram. We're going to get a lower orbital here. It's going to wind up sigma bonding. That's where the two electrons go. Then we'll wind up with an intermediate bonding, and then we'll wind up with a high energy anti-bonding orbital. So let's kind of look mathematically to see how this comes from. Okay, so here is our picture, first of all, for our bonding orbital. We're going to say there's a wave function psi. It's going to be a combination of lithium atomic orbitals from the 2s and 2pz, and to it we're going to add the hydrogen 1s orbital. And so just to begin, let me point out that if the two coefficients are the same, we would have a covalent bond. This is what you learned in freshman chemistry, when the electrons are shared equally between two nuclei. If the CH is 0, and we don't have any hydrogen component, then that means that the electrons are totally both on the lithium atom. Hydrogen has lost an electron, lithium has gained an electron, so we'd have lithium minus H plus would be our configuration. If the lithium coefficient were 0, it'd be just the opposite. Both of electrons would wind up on the hydrogen. Now, what might surprise you, in this actual molecule, the electrons prefer more to be on the hydrogen. And when we go back and look at the diagram, we'll see where it comes from. Lithium hydride is a nice vapor phase molecule that you can look at. It's very reactive. It'll react with water, stuff like that. But it is something that has been thoroughly studied. Okay, so here's our problem. We have a total of 3 orbitals, 2 on lithium and 1 in hydrogen, that can participate in the bonding. And if we start from 3 atomic orbitals, we have to wind up with 3 molecular orbitals. The MO diagram, the molecular orbital diagram, shows 1 bonding orbital, 1 anti-bonding, and the one in the middle we're going to see is mostly non-bonding. So bonding, anti-bonding, mostly non-bonding. But how do we get to that? So let's talk about hybridization. Unless you had a very unique organic chemistry teacher, he or she would probably have talked to you about sp3, sp2, sp hybrids, but never about things like S0.8, P0.2 hybrids or anything else like that. In the real world, there are very few sp2, sp3 hybrids. Methane happens to work for sp3 hybrids. Ethylene does not really work for sp2 hybrids, even though that's what you would have been taught, and I'll show you also why it does not. Anyway, the lithium hydride molecule, like all molecules, are very smart. They find their lowest energy orbital, and the way it's going to do it is you can mathematically say the lithium creates a hybrid, which is 0.813 of the 2s orbital in lithium, and 0.582 of the 2p orbital. So quite a bit more of the 2s than the 2p. And that'll be a significant point that I'll want to make. If I then take this definition and I want to know the entire orbital, and I plug into what I had up above, I wind up wanting 0.397 for the coefficient on the lithium orbitals, 0.685 on the hydrogen. And I can simply then plug in what this hybrid is, and so our total molecular orbital, this is the bonding one, looks like this. And so an important point is we can create this orbital without ever talking about hybridization. Physical chemists, such as I, who like to talk about molecular structure and bonding, kind of think of bonding as the witches with a cauldron. They throw all kinds of snails and puppy dog tails into there. Physical chemists throw all kinds of orbitals in a pot, let the pot stew, and the soup that we create is going to find the lowest possible energy of the orbitals that we have. So this is a computational result, but it's very well verified by what experiments have been done on the lithium hydride. So we never would have had to talk about hybridization. We could have just written this structure here. Okay, but that said, and as you saw from organic chemistry, the concept of hybrids can sometimes help you understand bonding. So what I showed you before were the lithium orbitals on the left, hydrogen atom on the right, and then this was the molecular orbital diagram. And we had a hard time understanding where this middle orbital comes from. If we now decide that we want to make two sp hybrids, they would each have an energy in between the 2s and the 2p orbitals. So we would create two hybrids here. The other 2p orbitals are pointing away from the hydrogen, and so we're not interested in them. So let's see how this works. So let's create this hybrid. We'll take the 2s orbital and the 2p orbital. Now keep in mind, I'm going to stick this right on top of that one. I'm not going to try to bond the plus to the minus. I'm putting it right on top. And so that's going to enhance the plus wave function on the right side of the hydrogen nucleus. And a lot of the left side will get canceled out by plus wave function and minus wave function. So our hybrid, the sp hybrid, winds up pointing towards the right. If I bring up my hydrogen 1s orbital, these dotted lines here indicate the bonding that we have. A lot of negative, well, did I draw a picture of it? I guess I didn't draw a picture. But look at these things, two things being smushed together, and then you're going to have a lot of negative charge between the two nuclei. When you do this, you also create the other hybrid. And the other hybrid would point in the opposite direction, and it has nothing to do. It's pointing away from the hydrogen atom. It's nothing to bond to. So if we created these two hybrids, one of them can bond, and that would be this bonding right here. That's our bonding orbital. The other hybrid would wind up here in the middle as a non-bonded hybrid. But notice it's different in energy from the atomic 2s orbital or the atomic 2p orbital. So the hybrid picture helps us understand why it's somewhat in the middle, but it misrepresents the picture because we're taking a lot more of the 2s orbital than the 2p. So mathematically, this is what we had. If you square these numbers, this is about 65%. The 2p orbital is about 35%. So I don't know what your organic chemistry professor would want to call this hybrid, but it's certainly not strictly an sp hybrid. One thing while we're talking about it, well, let me skip over this, but for now. Let me, in the 1 minute that I have left, just point out again that hybrids are artificial creations. So when we made these on the lithium atom by itself had no reason to create hybrids. It's only when the hydrogen atom approaches it, lithium is encouraged to take 80%, or actually the correct number was 65% of the s orbital and about 35% of the p orbital and create something like this. And then we can bond it to the hydrogen atom. So make sure you understand a hybrid is an artificial creation. A molecular orbital is actually what is formed when atoms combine to form these molecular orbitals. And we can look at them as combinations of orbitals or orbitals to hybrids. So in the example that we talked about for HF, we had a p orbital combining to the 1s orbital, and we created the bonding orbital, the sigma bonding orbital for HF. Well, in the 12 seconds I have left, and I'll come back to this again after we have our exam, let me just point out to you why things like sp3 hybrids don't work. Methane, all of the bonds are equivalent with 1/4 share s orbital, 3/4 share p orbitals. But what if we have methyl chloride? It turns out chlorine does not very much want to bond to a carbon s orbital, even if it is a 2s orbital. And mostly the chlorine is going to bond to a p orbital. And so the CH3 part down here, if anything, this is more like an sp2 orbital, and then the p is pointing up towards the chlorine. Those aren't going to be exact numbers. Maybe this is 80-90% p orbital carbon to chlorine, and maybe 10 or 20% of the p orbital is bonding to these carbons. But I think you can see quickly why talking about pure hybrids, sp3, sp2 doesn't work. Well, on Friday, I'll also tell you why the SP model does not work accurately for acetylene. It gives you a pretty picture and you can understand the structure, but the representation of the bonding comes out to be inaccurate. Okay, if you have any questions about the exam coming up, you can tell me or now, or ask me now, or you can send me emails and I'll try to answer on time. Okay, please study, do your practice problems.